Okay, so we have been talking about universal gravitation, and this exercise will help us assess our knowledge of gravitational fields and ratios. This one says, Earth is 1.5 times 10 to the 11th power meters from the sun. Pluto is 5.9 times 10 to the 12th power meters from the sun. Don't forget, Pluto is a dwarf planet. What is the ratio of the gravitational field of the sun on Pluto? G sub SP. SP means sun to Pluto. Compared to the gravitational field of the sun on Earth, G subscript sun to Earth. That's what the letters. Okay. Before we start writing down what we know, let's think about the field. Okay. So the gravitational field on Earth is pretty much constant. Every object falls at the same rate, and you guys know that is 9.8 meters per second squared. We use the lowercase g for acceleration of gravity. Okay, that's the field, the gravitational field. So when we draw a field, we use arrows. And we can know that the gravitational field closer to the sun will be greater. So for instance, Mercury would feel a greater gravitational field because of the sun than the Earth. So now over here with the Earth is going to be a little smaller. And then where Pluto is going to be even smaller. So that we can safely assume that the answer we get, the ratio, is going to be a small number. Okay? A small number. Okay, so how do we know that the gravitational field is greater as you get closer to the Earth? Well, before we solve that, let's write down what we know. So we were given the distance from the Earth to the sun, and the way in which we're going to describe that variable is with the letter r. So we're going to say distance r, sun to the Earth. And that was 1.5 times 10 to the 11th meters. Then we know the distance from the sun to Pluto. That was 5.9 times 10 to the 12 meters. Okay. Why are we using the letter R? We know that the equation, the formula for universal gravitation, gravitational force is universal constant times big mass or mass 1 times the other mass divided by the distance squared. That's why I'm using the letter R. Okay? Now let's think about the field. In this case, since we need to find the ratio of the field from the sun to Pluto compared to the gravitational field sun to Earth, is going to look like this. Okay? So gravitational field, we use an arrow showing that it's a vector field of sun to Pluto to G, sun to Earth. Another way you can write this one is by means of a ratio, like a fraction. So this will be gravitational field sun Pluto divided by gravitational field sun to the Earth. That's what we're trying to find. And now, how do we find this G? Well, that's very simple. Think about the Earth. The gravitational field on the Earth, we call it the acceleration of gravity, right? Everything accelerates at that rate. So the gravitational field is felt by means of, on the Earth, by means of the mass of the planet. So we have to use Newton's universal law of gravitation, this one here. And what we feel is our weight. An object falls because it has mass, and the weight is what pulls it down. And we know that weight is equal to mass times acceleration of gravity. And the weight, another way to call it weight, is the force of gravity on the object. I want you to see that these two are both gravitational force. So we can set them up equal to each other. These two. Sorry. These two. Whoops. So we'll get mg for any object on Earth is equal to universal constant. In this case will be the mass of the Earth times the mass of the object divided by the radius of the Earth squared. That's the distance to the center. Okay, this is for the Earth, the gravitational field on the that you feel because of the Earth, or I feel, or anything feels. Notice that the mass of the object will cancel, and then we get that the gravitational field is the universal constant times the mass of the Earth divided by the distance squared, the radius of the Earth squared. To show that it's a field, we'll draw the arrow. And the most important thing to take from this is a constant, universal constant. The mass of the Earth is not going to change. So truly the only thing we can change is the distance, right? You can get farther away if you go to space, you get to the International Space Station, or if you were to go closer to the center of the Earth, right? If you could do that, then that you can change. So that tells us that the gravitational field is proportional not to the constants, but the one thing you can change. So the gravitational field is proportional to 1 over r squared because the distance is the denominator. This is the inverse square law. We already knew this, right? The closer you are to the center of the Earth, the greater the field would be, and then the farther away you're from the center, the weaker it'll be. And it just proves what we said over here, that the gravitational field on Pluto is going to be less. Okay, inverse square law. So now we're going to do the same, but with the sun and the planets. Okay. So capital M is going to represent the mass of the sun. So gravitational field, we're going to use this formula. This one here. Gravitational field of sun Pluto. That's going to be capital G, mass of the sun, divided by the distance between the sun and Pluto. Likewise, the gravitational field for sun and the Earth is going to be gravitational constant, mass of the sun divided by the distance between the sun and the Earth. All right. So to find the ratio, we're going to divide this one over this one. So we can say gravitational field, sun Pluto, I'm just going to say SP over gravitational field SE is equal to this. Let's cancel things out. Gravitational constant cancels, the mass of the sun cancels, and this is what we get. 1 over this distance divided by 1 over this other distance. And then we simplify, you're dividing fractions, so you can just, instead of dividing by this, you can multiply by its reciprocal, you can use the cheeseburger method, whatever you want to do there, okay? So that means we'll get that the ratio between the gravitational fields is going to be the ratio between the distances, but flipped. Instead of having the Pluto distance as your numerator, you're going to have it as your denominator. So then if we plug in our numbers, we'll get, oh, I forgot the square on all of them. Sorry. Don't forget to square. So then we'll have 1.5 times 10 to the 11th meters. The square goes outside, divided by 5.9 times 10 to the 12 meters. Don't forget to square. Now we got to use decimals. It's a ratio. The units cancel. We're just going to get a number. So 1.5 times 10 to the 11th squared. 5.9 times 10 to the 12 squared. There you go. So the answer is let's round to 6.5 times 10 to the negative 4. So that's a small number, very small number. If we write it out, we'll get 0.00065. Like we said, a small number. The gravitational field felt by Pluto because of the sun would be a lot less than the Earth. This much less. That's it.